Welcome back. So this is lecture 45 in this course on Bayesian data analysis for behavioral sciences. The topic of this lecture is interaction effect and nested contrast in regression modeling. So this is an important topic in regression modeling because you wouldn't always have, let's say, just a single predictor in the model or a single factor that you would want to test, right? You might have hypothesis that would require you to test the effect of multiple factors at the same time. So you can have a single model that includes, let's say, more than one factor in a single regression model. Okay, we saw one example in the previous lecture where we include word type, that is word or non-word, and the frequency of the words as predictors. Right? But not only that, you can have other kind of, you can have hypothesis about interactions of several factors. So for example, let's say, let's think about a simple example. So let's say the population is increasing in let's say overall human population is increasing at some rate. So let's say we want to model at what rate human population is increasing. So on y-axis you would have number of people, and on x-axis let's say you have time. Okay, so you can have one hypothesis about the rate of increase of population, right? So at exactly what rate population is increasing, but you can have hypothesis about whether the rate of increase in population differs across countries or across continents, or let's say it's another factor like geography, right? Now geography is another factor, so you can test whether in certain geography population increases at a faster rate compared to some other geography, right? Now this is a different kind of hypothesis, because on the one hand you still want to test the hypothesis whether overall human population is increasing with time, but you also want to test whether this rate of increase is faster, let's say in African continent compared to, let's say, European continent, right? To test this kind of hypothesis, you will need to have some interaction effect parameter or nested effect parameter. Okay? Let me illustrate how. So let us come back to our example that we took in the previous lecture. The task participants have is this, that they want to recognize a word on a screen. Okay, so let's say on a screen they see something like a string like BKTR, and their task is to recognize whether it is a meaningful word or not, right? So they would say yes if it is a meaningful word, or no if it is not a meaningful word, using some keyboard keys, right? And what we are interested in recording is how much time do they take to recognize this string, so their recognition times. Okay, in the previous model we tested two hypotheses. So one hypothesis was that words are, so let me write it like this, words are recognized faster compared to non-words, and second hypothesis was that high frequency words are recognized faster compared to low frequency words. Okay, good. So these were our hypotheses. Now it's straightforward to test hypothesis 1, because all you need is a factor which basically tells you whether the string is word or non-word, and then we can directly compare recognition time in words versus non-words. So how we will do it? Using a regression model. So we can simply have a model like this, that recognition time for ith string comes from a log normal distribution with parameter mu I and sigma, where mu I equals to alpha plus beta into string type for the ith string. So whether string type is word or non-word, which you can encode as 1 0 or minus 1 plus 1. Okay, but the point here is that, okay, so let us, before going into hypothesis 2, can we think of the workflow of regression modeling? So what are the steps you will take? So let's say you already have some word recognition data, as CSV file. So let's say you have some data file in CSV format. So you have already collected this data from, let's say, 40 subjects, where each subject reads 250 words and 250 non-words. Okay, so that's your experiment design and that's your data. That's the kind of data you collected. So you will have recognition time for 500 strings for each participant. So it's a lot of data. Okay. Now, what do we do with this? So we have data. Now, how do we set up regression modeling, or how do we test this hypothesis in the Bayesian framework? So we need some workflow, some step-by-step procedure to do this, right? So this is something you can think, because you have we have developed these ideas that what is important for inference, right? So you can think that what will be our workflow. So you are given data, you have experimental data, what we would do now. Okay. So first thing to do, of course, is to make assumptions. Okay. You need to list down assumptions. Okay. Without assumptions, there is no inference. That's in fact the first critical step in inference, right? And these assumptions do not even require data. So you make these assumptions before even looking at the data. So you cannot make these assumptions after looking at the data, right? So first thing you need to do is to make assumptions. What kind of assumptions do you need? Likelihood assumption and the prior assumption in Bayesian modeling framework. So you need some likelihood assumption and prior assumption. What would be your likelihood assumption? What you can assume, so this, I'm not going to go into reasoning of this, but this is what we have been assuming for this kind of data, that recognition times for ith string comes from a log normal distribution with mean mu I, standard deviation parameter sigma, right? Where mu I itself could be a function of some other predictors in the model. Okay. Now this is the point where you can encode your hypothesis, right? This is what we do in linear regression modeling, that on the parameters of your distribution, you can set up, you can basically represent your hypothesis, right? So how do I represent the hypothesis here? So for example, one hypothesis you had was this, that on average recognition time changes as the word type changes from word to non-word, right? So let's say word type is indicated by type I. So I encoded that hypothesis. Okay. Let us just go with H1 for now. So this is our likelihood assumption. Now we need prior assumptions on 3 parameters of interest. What are the parameters of interest here? Alpha, beta, and sigma. So we need some priors on alpha, beta, and sigma. Okay. So we have already made assumptions. Okay. Now second thing we need to do is do some prior predictive checks. So this is not an essential step for inference, but this is always a good practice to do a prior predictive check. The utility of prior predictive check is this, that it can give you some good insight about how good your priors are. So if your model is allowing huge range of predictions, that means model is not well constrained. So let's say model can predict anything between 20 milliseconds to 10,000 milliseconds as word recognition time, and that's a bad model. That means the model is not properly constrained. That can happen when you have totally uninformative priors, and priors are not good, right? So you want model to be reasonably constrained in its predictions, right, in its prior predictions. So it is always a good idea to check prior predictions of the model. Okay, fine. So once you generate prior predictions and see whether they are in reasonable range, now your model is ready. Now you can use the data to do what? To estimate model parameters. So you can do the parameter estimation step. How do we estimate model parameters in the Bayesian framework? We need to estimate posterior distribution, right? So we'll need some computational approach, right? So let's say Hamiltonian Monte Carlo or MCMC algorithm. We had an easier way, so we can use BRMS package. So we can set up the model in BRMS, something like this. RT comes from, let's say, 1 plus type, family will be log normal, right? So that's likelihood, then you can set up priors and other things. So when you run this model, this will give you posterior distribution for these 3 parameters of interest. Okay. So from these posterior distributions, you can calculate 95% credible interval and other things, right? Now you can interpret posterior distributions or 95% credible intervals. How do we interpret them? 95% credible interval tells you that you can say with 95% certainty that the true value of the parameter lies within that in A and B, so lies within that range. Okay, that's it. It does not tell you whether there is evidence for this hypothesis or not. It just tells you about the true value of the parameter, but it can give you a good sort of indication whether what you have predicted, what your hypothesis predicted, is supported by theory or not, right? In order to do that, you should of course think about what does your hypothesis predict about the parameter values, right? About the true parameter values. So for example, what was your hypothesis? That words are faster than non-words. So it is so words will be recognized faster than non-words. So if type is such that you are encoding words as 1 and non-words are 0, okay, that means beta, so this is what your hypothesis predicts, so beta should be less than 0. And let's say you get a posterior distribution such that the 95% credible interval for beta is minus 40 to minus 10, then you can say that data supports your predictions. Okay. After that, you will of course need some model comparison to claim evidence. So that part we haven't covered yet. So I haven't taught you how to do model comparison, but that will be your workflow. Okay. And after that, you can also generate posterior predictions from this model. So what this model will predict for future data. Okay. So fifth step is posterior predictions. So we can generate posterior predictions from the model and compare it against some future data, and then we can do model comparison against competing models. So this is the step that where you do proper hypothesis testing, as well as you do you can test, you can compute evidence for a theory. So let's say evaluate or quantify evidence for a theory, right? So quantify evidence for a theory or assumptions, right? So this is the workflow of Bayesian regression modeling. Okay. Now let us come to the main point of this lecture, which is interaction effect and the nested contrast. Okay, why does it matter? Okay. So let us think that for the same task where people have to recognize whether the words on a screen is a proper meaningful word or not, okay, we have actually hypothesis about words mainly. About non-words we do not have very good idea, except that words will be recognized faster than non-words, right? So let us consider these two hypotheses about words. Okay, H1, that high frequency words are recognized faster than low frequency words. Okay, so high frequency words would have faster recognition times compared to low frequency words. Okay, which is a reasonable assumption. Okay. So this is hypothesis 1, and this has been tested over multiple studies in multiple languages, right? So let's say you collect some data for, let's say, recognition times data from an Indian language. Okay, we talked about the data just before. So let's say you already have that data and we want to test this hypothesis. Okay, but there is another hypothesis in literature, which is this, that shorter words, so words that are shorter in length, so for example, let's say words with just 3 letters are faster to recognize compared to words with, let's say, 7 letters, right? So shorter words are faster to recognize compared to longer words. Now, this is another reasonable assumption or reasonable hypothesis, because it could be the case that for longer words you will need to encode lot of unique basically phonetic sounds in your memory, and you also might need to do integrations, right? So shorter words that way would be faster to recognize, right? So that's another hypothesis. The shorter words are faster to recognize compared to longer words. Okay, now this makes sense. Okay? So you have two hypotheses. One is about frequency effect, another is about word length effect. First is high frequency words are faster in their recognition times, and second is shorter words are faster in the recognition times. If I ask you how would you test these two hypotheses in a single model, I think you can easily come up with a model. So let's say you have you subset data only for words, and you make these assumptions that reading time for ith word or recognition time for ith word comes from, I'm not saying ith is string, ith word. So we are only analyzing word data because our hypotheses are only about words. Comes from a log normal distribution with mean mu I, standard deviation sigma, where mu I can be written as alpha plus beta 1 into frequency of the ith word plus beta 2 into length of the ith word. So beta 1 will give you to what extent frequency affects recognition times, and beta 2 will tell you to what extent word length affects its recognition time. Okay. So when you fit this model, now how many parameters do you have? Alpha, beta 1, right, beta 2 and sigma. So when you fit this model, you will get posterior distribution of these 4 parameters, and you can interpret beta 1 and beta 2 to make a claim or to check whether the predictions are consistent with your data or not. Okay. So this is fine. But what if someone makes another hypothesis, let's say H3. Hypothesis 3 says that the frequency effects are stronger, or let's say the frequency effect is stronger for short words compared to long words. What does this mean? What this statement is saying is that there is some effect of frequency on word recognition times. What is the effect? What is the hypothesized effect? That as frequency increases, word recognition time decreases. So basically recognition time gets faster. So that's the frequency effect, right? So you can represent the frequency effect like this, that if frequency is on x-axis and recognition times are on y-axis, right? So as frequency increases, recognition time decreases. I'm drawing a linear line, but it wouldn't be exactly linear if you take, let's say, log RT, but that's the idea. So as frequency is increasing, the recognition times are decreasing. Basically, recognition times are getting faster. So that's a frequency effect. Okay. So this is what this term means, frequency effect. Next part of the sentence says that the frequency effect is stronger for shorter words compared to longer words. So suppose you draw 2 lines, one only for short words, or let's say relatively short words, and you draw another line for long words. Another line, by another line I mean the relationship between frequency and RT for long words, right? What this statement means is that for longer words, if this is the slope for short words, for longer words, this slope would be something like this. So not below this, because long words would be relatively slower. So, for the longer words, the slope would be something like this. So, let's say this is for longer words and this is for shorter words. This is what this hypothesis is saying, that frequency effect, which is represented by this line, line plot between frequency and RT, it's saying that frequency effect is stronger in shorter words compared to longer words. That means this relationship, which is basically represented by the slope, right? So, this slope is higher in shorter words compared to longer words, right? So, for shorter words, the recognition time would decrease sharply as frequency increases compared to longer words, where recognition time would decrease slowly as frequency increases, right? So, the statement is about the difference in slope or the difference in frequency effect between short words and long words, right? So, let us say some parameter beta 11 represents the slope between frequency and RT for short words. Okay, so let us call it beta 1 short, and beta 2 short represents the slope between RT and frequency for long words, right? So, it is the difference of beta 1 and beta 2. Okay. So, what this hypothesis is saying is that this difference between these slopes would be positive. Okay. So, you will have slope of this line for shorter words, there would be slope of this line and there would be some slope of this line for long words. If you take the difference between these two slopes, that difference would be positive. Okay. Consider another scenario where this is the relationship between frequency and RT for short words, and this is the relationship between frequency and RT for long words. What does this graph represent? This graph is telling you that there is some effect of frequency, that as frequency is increasing, recognition time is decreasing for both short words as well as long words. Okay, so that's the one thing that plot is telling you. Another thing the plot is telling you is that on average, long words are shorter compared to short words, because this line representing long words is above the line representing short words. So, the long words are slower to recognize. That's the second thing. Third thing this plot is telling you is that these two slopes are equal. These two lines are parallel to each other. What does that mean? That the rate at which recognition time decrease with frequency, you can call that rate the frequency effect. What is the frequency effect? The rate with which recognition times decrease as frequency increases, right? So, that rate of decrease in recognition time with frequency, that rate is exactly same in short words and long words, because these slopes are equal, these lines are parallel, right? That means this, if your data is of this type, let's say you have these parallel lines between long words, short words, then your data is not consistent with hypothesis 3. That means frequency effect is not stronger for short word compared to long words. It's actually equally strong in long words and short words. Okay. So, this hypothesis 3, how do we test this hypothesis 3 in a linear regression model? You got the idea that what does this mean, right? This is something like you're comparing slopes for short words versus long words, right? So, that is fine. So, you're comparing frequency effect in short words versus long words, right? But how do we test it in a linear regression model? Okay. Let us explore that. So, let us rewrite our assumption. The recognition time for ith word comes from log normal mu I sigma, where we wrote mu I like this: mu I equals to alpha plus beta 1 into frequency for the ith word, beta 2 into length, word length for the ith word. So, up to this point the model tests hypothesis 1 and hypothesis 2, but it does not test hypothesis 3. What was hypothesis 1? That there is an effect of frequency. Hypothesis 2 was that there is an effect of word length. But hypothesis 3 says that frequency effects are stronger for short words compared to long words. How do we test that? So, let us reread this statement. Frequency effect is stronger for short words compared to long words. Okay, what are we talking about? The frequency effect, not the recognition time itself. We are talking about the frequency effect. What parameter in this model represents the frequency effect? In this model, what parameter represents the frequency effect? Beta 1, right? What the hypothesis is saying? That this beta 1 is actually not constant. Beta 1 itself changes as a function of word length. That this beta 1 should be stronger for shorter words, or let's say beta 1 should be larger for short words compared to long words. The magnitude of beta 1 should be larger for short words compared to long words, right? So beta 1 itself is a function of word length. Okay, so it's definitely not constant, so you cannot just keep writing it beta 1. What we can do, we can write beta 1 I. So beta 1 for the ith word, right? Now you can write beta 1 I equals to, so this itself is a function of word length. So let's say alpha dash plus some slope parameter beta 3 into word length for the ith word. So what I did, I write mu I is equals to alpha plus beta 1 I into frequency I plus beta 2 length I, and then beta 1 I itself is alpha dash plus beta 3 into length I. Okay. Now this model is testing several things. One, this parameter, so this is a parameter now, alpha dash. So this parameter would tell you the effect of frequency on recognition times when length is 0. Basically, you will code length as -1, +1 or 0, 1 when you have high short words and long words, right? So this tells you the main effect of frequency when length is 0. Beta 2 tells you the main effect of length when frequency is 0. Beta 3, what does beta 3 tell you? Beta 3 tells you what is the effect of word length on frequency effect. To what extent frequency effect increase or decrease as word length changes. Okay. So let's say you take word length as -1 and +1. -1 when the word is short, +1 when the word is long. Okay. Or the other way around, whatever you take. So what it would mean is that this parameter beta 1 I would be alpha plus beta 3 when word is long and alpha minus beta 3 when word is short. Okay. So this is what will happen. Okay. So beta 3 is actually telling you the difference of frequency effect in short words versus long words. Okay. So this is the model that tests hypothesis 1, that what is the effect of frequency using this parameter, hypothesis 2, what is the effect of word length using beta 2, and hypothesis 3, which is about whether frequency effects are stronger in shorter words compared to long words using this parameter beta 3. Okay. So if beta 3 is 0, so let's say you get a credible interval which suggests that beta 3 is 0, the true value of beta 3 is 0, that means that the data does not support hypothesis 3. That means frequency effects are not stronger in short words compared to long words. They are comparable. The frequency effects are equal in short words versus long words. So beta 3 would be 0 if these lines are parallel, if you are in this situation. And beta 3 will be positive if you are in this situation. Positive or negative depending on how you set up the contrast. How you set up these -1, +1, these numeric values of these predictors, right? This model is actually called an interaction effect model. So you have two predictors. So you are testing the main effect of frequency and length, and you are also testing their interaction effect. Okay, so this is actually called interaction effect. Beta 3 is called the interaction effect parameter. What is interaction effect? Basically, it's the slope of difference. Basically, it's a slope, the difference of slopes, right? So if let's say one of the main effect that you are testing is the main effect of frequency. So, to what extent frequency affects recognition times, right? Now, let's say you have another predictor, which is the word length. So, you are also, let's say, interested in whether for shorter words the frequency effect are stronger compared to longer words. Okay, then you test it by testing the difference of their slopes, right? So, difference of slopes is actually the interaction effect. Okay. In another way, you can write it like this, that let's say average recognition time for high frequency words is this, and average recognition time for low frequency word is this. So, if you take the difference on average, difference of let me put a bar to indicate the average difference. So, this is, let's say, on average recognition time of high frequency word. This is average recognition time for low frequency word. So, this difference indicates the effect of frequency, to what extent frequency affects recognition times. But if, let's say, you calculate this effect for short words and then you calculate the same effect for long words, same thing for long words, right? So, the difference of this difference is the interaction effect, is the extent of interaction effect, is the magnitude of interaction effect. If this is 0, if this difference is 0, then there is no interaction effect. Hypothesis 3 would not be supported. Okay. So, we test the interaction effect using a model like this, right, where we set up, because hypothesis was about frequency effect. So, whether frequency effects are stronger or whether frequency effect change as a function of word length. So, we set up frequency effect as a function of word length, right. You can of course write these two lines in a single line by just plugging in. So, you can just plug in this thing here, right. So, you can write this whole thing in a single line like this. So, RTI comes from log normal mu I sigma, and mu I is equals to alpha plus, let us plug in this thing, alpha dash plus beta 3 into length I, okay, plus beta 2 into into length I into frequency I, and then beta 2 into length I, right. I just plugged in this beta 1 I in this equation here, right. So, if you expand it, the equation becomes mu I equals to alpha plus alpha dash into length I, alpha dash into frequency I plus beta 2 into length I plus beta 3 into length I into frequency I. Okay. You can actually rename this parameter as beta 1, okay, just for simplicity you can rename this as beta 1. So, alpha plus beta 1 into frequency I plus beta 2 into length I plus beta 3 into frequency I into length I, where beta 1 indicates main effect of frequency, beta 2 indicates main effect of length, beta 3 indicates interaction effect of frequency and length, right. But it is a vague term, interaction effect is a vague term. You should understand what does this interaction effect mean. So, that is what I tried to explain, that interaction effect is basically the difference of slopes, and you apply, you test for interaction effect when you have a hypothesis like this, that the frequency effect is, for example, the effect of a predictor A is stronger for certain type of stimuli compared to another type of stimuli, right. So, in that situation you can test for interaction effect. So, in this case frequency effect is stronger for short word compared to long word. That was our hypothesis. Okay. Now, interestingly, it may be the case that you have a hypothesis which is not really about interaction effect, okay, but you might get misled into believing that this is about interaction effect. When that can happen? So, let us say you have a hypothesis, let us call it H4. So, let us say your hypothesis is like this, that frequency effects exist only for short words and do not exist for long words. Okay. So, frequency effects occur only for short words, not for long words. What does this hypothesis mean? That frequency effects would be there, would be as expected for short words, but the frequency effects for long words will be 0. So, if you draw it graphically, this is what it will represent. This is what it would mean, that for short words frequency effects are as usual. So, this is for short words, but for long words the graph is totally flat. So, for long words there is no effect of frequency. So, precisely this is the kind of relationship we expect. Now, you can't test it using an interaction effect, okay? Because even let us say interaction effect tells you that there is a difference between the two slopes, that does not imply anything about whether long words have a flat slope or let us say a slightly negative slope or positive slope, right? You can have a difference between slope in so many conditions, like you can have a difference between slopes even if the long word line is going upwards, even then you would have a difference between slopes, okay? So, the interaction effect, which is testing the difference between slopes, would not precisely test this hypothesis. It can test hypothesis 3, because hypothesis 3 is only about the difference in slopes, but here we care about each individual slope. So, whether slope for short frequency word is negative and slope for long words is flat, basically 0, right? So, that is what we want to test. So, how do we do this? How do we test this hypothesis? Well, one way is to you separately test the hypothesis for long words and short words. What that would mean, that you split the data into long words and short words and then test this hypothesis, but that is not a very good way. In that method you are losing power, you are losing half of the words, and then you are fitting separate models onto subsets of data, right? But there is a more natural and easier way to do this in a single model without losing power. How we can do that? Using nested contrast. What I will do is this: I will set up contrast in such a way that it tests a hypothesis, frequency hypothesis only for word, and then frequency hypothesis, first it tests a frequency hypothesis only for short words, and then frequency hypothesis only for long words, and measures a common intercept. So, average recognition time across all short as well as long words, right? So, single model, I will set up their numerical values of predictors in such a way that it tests all those hypotheses. How do I do this? I will need to come up with 2 predictors that can directly test my hypothesis for, right? So, one predictor I will set up will be frequency within short words. And how would I set it up? Frequency within short words will be given by if else length is short, okay, and frequency is, let us say, high frequency, okay, then I will set up the contrast +1. Else, if this does not happen, then I will again check if else length is equals to short and frequency is equals to low frequency, then I will set up the contrast -1, otherwise 0. What this would do is this, that all the words which are long, okay, so for all the words which are long, it will set up this predictor as 0. So, this is for long words. So, this predictor will have value 0 for long words. It would have value -1 for short low frequency words, and it will have a value +1 for short high frequency words. Okay. Similarly, I will set up another predictor, frequency within long, which will have values like this: 0 for short words, -1 for long words which are high frequency, long high frequency words, long and low frequency words, and +1 for long high frequency words. Okay. So that whatever estimate you get for this predictor, it is only testing the difference of low frequency, high frequency words within long words, right? Because short words will be 0. So when you have these two new predictors, now you can set up a model like this. RTI comes from log normal mu I sigma, where mu I equals to alpha plus beta 1 into word length. So we will still test the main effect of word length. Then beta 2 into frequency. Now we are testing frequency effects, but frequency effects separately in long words and short words. So frequency within short, and then plus beta 3 frequency within long words. What this will do? Well, beta 1 is straightforward. This will be testing whether long words are slower than short words, so that is fine. Beta 2. So if let's say beta 2 is greater than 0 or less than 0, what that would mean, that there is an effect of frequency. So there is a frequency effect for short words, right? And if beta 3 is equals to 0, that would mean there is no frequency effect for long words, right? So it is directly testing our hypothesis 4. Okay, so depending on whatever estimates you get for beta 2 and beta 3, you are directly testing those hypotheses. So what is the frequency effect within long word and what is the frequency effect within short words? Okay, so it is directly testing that hypothesis, but within a single model without subsetting the data, right? This is called nested contrast. The contrast we are setting up here is called nested contrast, right? So contrasts this way are very important, especially for cognitive science, so for modeling in cognitive science, or for simple data analysis in cognitive science, because often we have predictors which are not numeric. These predictors are categorical predictors. So for example, you're testing for long word stimuli versus short word stimuli, or let's say you're testing for orientation, left, right, right? So these kind of effects we test. So these predictors are categorical, right? They have some categorical value. So we cannot work, so the model cannot work with categories. Let's say if you just feed the model short and long, it won't work. So the model has to, so you need to convert those categories into corresponding numeric value, right? So for example, you convert short word, you encode short word as -1 and long word as +1. Okay? So these kind of numeric values, so basically transforming categorical predictor into a numeric predictor is important. I mean, without that the model wouldn't work, right? But how exactly what kind of values we use to encode these categorical predictors becomes very important for hypothesis testing, right? So for example, if you give, so, and there are many other kind of contrasts, and these become more important when you go from one predictor to two predictor and their interaction and into more complicated hypothesis, when you have more predictors in your model, right? So it will, it's always a good idea to develop your understanding on contrast coding. So for example, here we saw how nested contrast is really useful for specific hypothesis testing, right? So I would suggest that you read on contrast coding. So if you develop some understanding on contrast coding, it will really help in regression modeling. Okay. So I will conclude the regression modeling lectures here. So basically, I think we have covered some examples and we have also covered interaction effect and nested contrast, right? So you have a fairly good idea of how to develop regression models in the Bayesian framework. We will of course take more examples as we go into model comparison and hierarchical modeling, right? We will keep doing more regression modeling examples, but I believe that you know how to develop a regression model in the Bayesian framework, so how to specify assumptions and how to estimate parameters using BRMS, right? So that was the goal for these lectures, right? Now from the next lecture onwards, I will start how to evaluate a model, how to quantify predictive performance of a model given the data. Okay? So the next lecture onwards, we will cover model comparison, which is an important part of this course, because that's where we will start how to quantify evidence and how to actually do hypothesis testing in the Bayesian framework. Okay. All right, I'll stop here. Thank you.